All right, next up is John Orlando from Epic Solutions. They are also a gold sponsor of the conference. I'm going to hand it off.
All right, thanks, Ben. Yeah, my name is John Orlando from Epic Solutions. I'm going to be giving a talk today on kind of the state of the art with size, weight, and power optimized software-defined radio. So if you're a Batman fan from the old days, this was the best I could do to kind of get a throwback to Batman and Robin from back in the day. So swap, boom, pow is what we've got. A little bit of background about me. So I've known I was going to be an engineer for a long time, and I'm super thrilled to be in a room full of like-minded individuals. I spent 11 years in the wireless telecom industry before co-founding Epic Solutions back in 2009. I've been working in the GNU radio space and kind of tangentially around it since about 2005. And a lot of the work we do that we'll talk about today kind of focuses on how do you really push the boundaries of making things smaller, doing more with less, and where is the tipping points where you can start to apply some of the SDR work that a lot of folks are doing here into the real world when you only have, say, a watt of your power budget or a couple of watts power budget for your whole system. So just one slide about us real quick, right? So we make little blocks, we build whole solutions, and then we do a bunch in the cellular space. I'm happy to talk more about it. Come to our booth, we can swing by. But let's get kind of right into the meat and potatoes of this, right? So size, weight, and power is something that gets talked about a lot these days as people have been wanting to take SDR and move it into a world where they're either portable, mobile applications, more deeply embedded applications, trying to get the CPU and the radio that much closer together. We've done, since we started, a bunch of work to continue to try to shrink these things down. We have a product called Sidekick, which is a mini PCI Express card. And last year at the GNU Radio Conference, we kind of teased our M.2 card, which is a size shrink of kind of a size shrunken version. These cards are as good as I think just about anybody has done out there in terms of really thinking about size reduction, power reduction, I guess weight reduction, you could think of that as well, but this is trying to cram as much as possible into as small space as you can get. So we've been shipping these cards for a couple years and provide GNU radio blocks for supporting them that are up on GitHub, so you can get a GR Sidekick block and slap it in and use this in any of your flow graphs. We also provide a handful of different examples that people can use for getting up and running with these things. But the cool thing is you can start to use them to think about the entire system shrinking down a bit further, right? You've kind of got these, looking at these as enablers, is what can you put around them to build a system that isn't necessarily an external box and a laptop. You can either put it in the laptop, or you can start to think about single board computers that are much smaller, having one of these cards acting as the radio front end. So kind of examples here, a little bit more, right? We're big on using the more integrated RFICs. We'll talk about analog devices and sort of their work that they're doing here to support. We are big fans of ZIF and the momentum that continues to come with the ZeroIF solutions. One of the downsides of making things small is that they get really hard, technically challenging to build, right? Like these boards are, end up pushing the limits as far as getting components in a very small space and using footprints that can be challenging to work with because you're putting the radio, you're putting FPGA, you're putting other interfaces in a square inch or so, right? So not a ton of space, or a little more than a square inch. Not a ton of space to have to work with. But by the same token, you get a complete antenna input on the edge all the way to high-speed PCI Express interface coming out the other end. So it is a true kind of antenna port to digitize samples interface with an FPGA that you can start to do work around. So it's good that it kind of pushes this forward in our head to see how can we use this as a building block, because building blocks is how we want to think about all these things. We want to think about modularity first and foremost when we're building these radio systems. So the radio is a piece of the equation. It turns out that mini PCI Express and M.2 kind of fit this mold really, really well because there's lots of other pieces in the universe that already fold into that exact same footprint, right? You've got hard drives in the MSATA form factor, you've got Wi-Fi and Bluetooth cards, you've got cell modem cards, so there's a whole collection of commercial off-the-shelf solutions that already apply to, that have already put time into thinking about how do you make them really small. So we like to look at this as how do we bring an SDR solution to stand right next to those so that people can have that as one of the tricks in their bag when they're building a system. So like standards compliant form factors, really big in wanting to be able to push that forward. It turns out that PCI Express is near optimal for this. It is fast, it is baked in to be able to support a reasonable amount of modularity. If you do it right, you can hot plug, so you can come and go as you need to. and you have an ever-increasing speed race of lots of other computer peripherals that want to be able to use faster and faster interfaces, so we can kind of ride the coattails and be able to support more capable SDRs in terms of what we can get through to the host system. So scalability is another big piece here. At the point where you have gotten the radio really small and you've got these other things really small, you want to start thinking about, well, how can I put a whole boatload more of them in a smaller space? And this is a problem that we think about a lot along with the modularity piece. And it turns out that there's relatively straightforward ways to start moving these things together, which has been I won't say an unexpected consequence, but we weren't sure how hard that was going to be. So being able to take 1 radio, 2 radio, 4 radios, 8 radios, we have customers, some of the folks even in this room, that are taking and scaling these things in really interesting ways to be able to build MIMO-capable systems out of them. You have all the same problems you would normally have as far as you've got to get reference clock and PPS to those cards, but at the point where you have the cards very small, you can start to take advantage and build systems that do things like support 8x8 MIMO in a little card that you just slap into your PC. And that building block is one of the enablers. Turns out, like I said, there's a whole bunch of other pieces on the computer side that they've spent a lot of time figuring out. How do we want to handle fast data rates? How do we want to handle DMA that help to support this in different use cases? But having the radio be small is a key piece of this. At the point where you have this much data flowing through, your CPU loading becomes this massive challenge you have to deal with, which if you've ever taken one radio and plugged it into a laptop and really opened it up, and seen 20 megahertz to 50 megahertz of spectrum coming in, your CPU can very, very quickly choke. So multiply that by 8 receive or 8 transmit, and things come to a grinding halt really quickly if you want to do anything with any appreciable bandwidth. So part of the SWaP consideration on the whole is figuring out how to get that processing reduced as close to the antenna as possible, right? I know this isn't shocking in any way, shape, or form, but it's a problem that we spend a lot of time thinking about because we want to push the envelope in what's happening with these smaller radios. And I'll mention antennas as well because this is like the practical side of having to deal with these systems, right? If you tried to put 8 receive and 8 transmit antennas on this, it would be a relatively tricky thing to work out. There are ways to do it, of course, and I think we look at it as we're trying to get most of the hard stuff knocked off, and then the mechanics and the kind of the physics of how you're going to interact with that last antenna bit is something that can be managed, and people do figure out ways to make it work. So I mentioned before FPGA processing, and I know there's been a bunch of talk about RF NOC, and that work is fantastic. I think we have a very similar mindset as far as what can we do to help the signal processing chain along the way by pushing some of the core pieces into the FPGA and making them more viable to work with. The challenge that we have often, though, is we're working with very small FPGAs and very size-constrained systems, so we have to think about the problem a little bit different, because thinking about it in terms of CPU capabilities, if you've got a single, dual, or quad-core ARM, you can very quickly, even though it's low power, you can very quickly run out of steam trying to do the processing. So the SWaP problem on the whole, you really have to think about the partitioning from day one. If your radio is going to be there, great. How does everything else up the line need to, what does everything else up the line need to do to be able to make sure that you're going to be able to solve the problem at hand? And how do you balance between CPU and FPGA? So this is kind of an example of where when we start thinking about running GNU Radio on platforms where we want to be more balanced and more optimized, right? The typical bottleneck here is not between the radio and an FPGA fabric, if that's in your system, and I'd say most of the systems people have here have a similar architecture to this, right? This is usually not the problem. You can usually make this go really damn fast. Usually the FPGA has a bunch of processing that it's going to do to try to help the problem along, or in some cases it may just be a pass-through, but as soon as it becomes a pass-through up to that CPU, you have this bottleneck of the bus that it's using, whether it's USB or PCI Express. And even PCI Express, you can start to choke when you really start pushing large amounts of data through it. And then the more likely bottleneck is just, okay, you've got your samples DMA'd up to the CPU. Usually that gets right into RAM, so you need to start thinking about what's your RAM bus speed, or if it's going into local cache, okay, I can get it into cache, but I can only hold so much. And you want to start churning on it as quickly as possible to get the data rate down. Right, so this entire lineup needs to be considered, and not shockingly here, what we find is that being able to have the FPGA as an accelerator to help us do that processing and whittle the data flow down to some meaningful rate makes a big difference in what you can do in the long run here. And this doesn't apply just to big FPGAs. This applies to small FPGAs as well. And it's really just a matter of partitioning the problem properly. So let's look at a couple examples here that could be interesting to this group. So this is kind of 3 real-world examples of looking specifically at how do you take I'd say a canonical software-defined radio thing that you want to do and move it to FPGA accelerating, and what kind of benefits can you actually realize from it. And then what does that look like as far as the system deployment and what's actually possible. So this is a little bit of an eyesore. This is a data modem called Simplelink that we developed internally for some testing applications that some of our customers use with our radios. Right? It's kind of a standard vanilla modem, QPSK modulation, interleaving, forward error correction. If you run this modem all in software and having your IQ stream going between the radio and the CPU, a single x86 core of kind of low-end-ish quality, we're not talking about high-end Core i7s, you will consume about 96% of a single CPU core doing this entire flow all the way up to like a ton-tap interface hanging out here, looking like an Ethernet networking interface. A bunch of those CPU MIPS go right here where you're trying to do packet detection. There's a preamble at the head of the packet. You spend some on the Viterbi decoder, and it just at the end of the day ends up taking up a reasonable amount of MIPS. So okay for running on a laptop or okay for running on a reasonably high-end CPU. We were looking at, well, what could we do to move this example down to much lower-end CPUs if we wanted to run it on that. Right, so we went through and we actually had an intern this summer go through and kind of look at accelerating some of this and primarily focusing on just one single piece, not going and accelerating any of the core signal processing, but just looking at the single piece of how do you do packet detection to gate samples properly. And it turns out, right, this makes a big difference, and it's a common theme among the vast majority of the signal processing problems that we encounter. If you can just figure out when to gate samples up to the CPU, you will find, in general, what we have found is a pretty substantial benefit across the board. So in this case, just having the FPGA do some relatively straightforward correlations and gating when those samples go up and letting all the rest of the signal processing flow exactly the way it is in software, we dropped the CPU load from 96% to 36%. And the rest of this, some of you may say, well, I'm surprised it doesn't drop more. I mean, this was coded in vanilla C. This was not using any SIMD acceleration. It was more of an example that we could provide to folks so they could kind of get up and running and see, get a couple of cards talking for some of their typical applications. So I would consider this a very simple FPGA accelerator that ends up having a pretty substantial impact on the type of system that you can deploy this into. Because it does mean you can start to move it into things like lower-end ARMs that don't necessarily have the same level of MIPS in front of you. Another area, we do a lot of work in passive wireless device detection. So the canonical problem that we try to solve for some of our customers is they want to know, without ever transmitting, they want to know more about radio devices that are going to be in the area. And we do a lot of work on the cellular side in particular. This is an example of a solution that we've developed for doing LTE phone detection. Right, so if you know anything about, there was a talk a little bit earlier about doing LTE downlink, and they mentioned what's harder, LTE downlink or LTE uplink. LTE downlink, you have to kind of be able to do a survey and understand broadcast channels coming over the air. If you want to start looking at LTE uplink, not only do you need to be able to understand some of those broadcast messages, you also need to be able to decode certain bits out of those broadcast messages to figure out how to apply them when you want to look at uplink. So LTE uplink is a relatively computationally intense process to be able to demodulate and decode, especially when you're trying to do it blindly. Typically, when a phone is idle and sitting there and not communicating with the network, it's never transmitting. As soon as the phone wants to wake up and send a text message or wants to check your Facebook account or whatever, the first thing it has to do is it has to send a request into the network to say, hey, network, I'm interested in getting a dedicated channel established. Tell me how to do that, and the network will come back and say, I can give you a channel on this frequency or with this resource blocks, and go over here and we'll start having a dedicated session going back and forth. So that process is relatively involved. We had a software implementation that was capable of doing it, and a x86 was just barely kind of able to keep up blindly in real time without having any knowledge of the downlink frame structure to be able to detect, demodulate, and decode the preamble and the PRATCH and the RRC connection sequence that happens between the phone and the network. So we looked at this and we said, well, okay, we've got a kind of server class platform with a radio that's in place, doing the processing, and it's pumping out, able to say, I see an AT&T phone, I see a Verizon phone, I see a T-Mobile phone. What if we want to start shrinking that down to smaller platforms where we don't have the higher-end CPU capability? So we did the exact same model we talked about, that Simplelink modem. We said, well, what can we move into Fabric that brings us a significant amount of CPU MIPS and makes the processing problem easier? So in this case, it's a very similar sort of solution here, right? We basically say, how do we detect the very first preamble properly? And as soon as we see the preamble on that pre-ratch come in, gate the samples up to software and let software kind of do its thing from there. The software processing flow is the exact same processing flow. In other words, that the flow of having to demodulate and decode is still all happening in software. The only thing that's happening here is that we don't burden the CPU sitting there constantly waiting for a phone to actually chirp up. So this basically lets us go from x86 down to relatively low-end ARM, I'll say medium-ish end to high-end, I guess, ARM embedded platform. In this case, this is a Freescale IMX6 quad-core CPU that can keep up with a real-time stream. We've actually got some other folks at another conference this week, and they let this run on the conference floor for the several days they were at the show, and we were detecting 30,000 phones a day, that full demod decode sequence of seeing who they're from and the entire kind of RRC connection establishment process. So this gives us a lot more insight into how many phones are around, what kind of phones are around, and then we can see, we can do it with lower end platforms instead of kind of server rack class solutions. So the similar mindset of just all we have to do is think about problems of doing very simple things in the FPGA, and we can radically reduce what we're capable, radically increase what we're capable of doing with these smaller platforms. Third example here is probably a little more near and dear to people's hearts here. There's been a GNU radio block for doing 802.11 A and G and P decoding for a while now, and it's been steadily getting more and more capability built into it. And the idea with this block is it provides kind of a reference design for doing Wi-Fi reception, and you can do some Wi-Fi transmission. It does not support kind of full bidirectional comms. The ACK turnaround time is a very challenging spec to be able to meet, to kind of have it be a full-time transceiver to support that. But it gets used a lot, and the folks that developed it seem to be continuing to make updates for it. It does use SIMD acceleration for some of the harder signal processing pieces. But in the end, it provides a pretty capable solution if you have a sufficiently fast processor to do the signal processing behind it. Because again, everything is in software. So we looked at this and we said, well, what can we do to enhance this further, move it down to smaller platforms that didn't have a laptop grade capability behind it. So this is the flow graph of what this looks like typically as of, I think, a week ago or so from the GitHub account. And there's kind of the similar sorts of things, right? There's kind of packet detection pieces. There's kind of some synchronization pieces that are trying to understand timing and understand where to actually start looking and correct for some of the errors possibly coming over the air. There's the frequency domain translation, and then there's kind of the whole path of doing channel estimation through the Viterbi decoding. So at the output of the Viterbi decoding, you're getting real bits that are essentially a Wi-Fi packet coming over the air. So looking at this in acceleration pieces, we've been kind of playing with several different things at several different stages, right? So stage one is doing nothing but moving frame detection into the FPGA fabric so that the CPU is not burdened on constantly looking to see, is there a frame, is there a frame, is there a frame? All of the rest of the processing in the PHY would still be up on the CPU, but it only gets IQ at exactly the time when it needs to get them to say, okay, there's something here to actually start processing. And again, depending on how busy your environment is, this could lead your CPU to being relatively idle, or it could lead your CPU to being relatively busy, versus the all-software approach where it's basically running constantly, just looking for anything that would have to, doing the computations for every sample to see is a packet coming in. So when a frame is detected, the flow, it opens up the floodgates to say, okay, samples can now flow up to software to let them be processed and kind of go from there. And from there on, all of the rest of this processing is exactly the same. We're looking at trying to see if we can get an implementation to actually work down in an ARM Cortex-A9 with just this piece being in Fabric. It's not, we're not conclusive yet, but it's something that we are actively pursuing to see, is that enough? More likely, what is going to turn out is that to say we want to be able to run this in a small embedded ARM with an SDR sit in front of it, we'll probably need to do more significant amount of the processing down in the fabric. So not just the frame detection, but several of the other stages that are needed to kind of get synchronized, including the frequency domain translation. So at that point, we're kind of encompassing all of the pieces up to here, and then handing the output of this up to a GNU radio flow graph from the FPGA, so that the only thing it's worrying about is doing the kind of the channel estimation down to and the demodulation all the way down to the Viterbi decoding on the software side. And so that looks to be very, very viable to have that in a very low, relatively low-end ARM CPU, so we can start shrinking down the size of these guys. There's kind of the home run here, if we really want to start getting aggressive, is to say, let's move everything in the PHY all the way through the Viterbi decoder down into the FPGA fabric so that the CPU is really looking at it more or less like a Wi-Fi card at that point. And there's pros and cons for why you would want to do more or less in the FPGA. Some customers are interested in the sample level timing of samples flowing in, and they want to see as much as they possibly can about that. Other folks say, I could care less about the sample level timing. What I really care about is just getting output that I can keep up with as much as possible, a real-time stream of packets coming in. And in this case, you basically would end up with more or less a handheld handheld SDR that had the full 802.11a and G solution in something that's going to be on the order of probably 5 to 6 watts in that ballpark to be able to process a single channel coming in. We're also looking at the possibility of doing kind of packet generation in Fabric as well, right? It's this turnaround time, which is the real challenging piece. And so we've got some ideas on how to be able to solve that. And once you're there, you really do have just a transceiver. It's no more just a listen-only device. You can start using it to interact with other 802.11 systems that are commercially available 802.11 systems. So this work is underway. I mean, if you're more interested, come talk to myself or one of the other guys at our booths. That's targeting Xilinx RTX XC7A50T, which is kind of a mid-size Xilinx FPGA that's in our Sidekick M.2 card. So yeah, we'll give you more details if you're interested. So as we talk about these platforms, and people, but previously when we were here last year, we had our little Sidekick guys that we were showing off. These cards are continuing to get used in different ways by ourselves and by our customers. There's more stuff coming down the road here to try to push the limits of what's possible in these smaller spaces. So we wanted to take a few minutes and go through these as well. If you're familiar with our Matchstick lineup is these little kind of candy bar sized boxes that have single board computer in them, that same Cortex-A9 quad-core CPU, plus one of our Sidekick cards. So one of the number one things we get asked about the most is we need to go below 70 megahertz. We want to go down to HF and be able to handle that. HF has a ton of challenges associated with it, but our Matchstick S12, which is, this is the first time we're publicly talking about this as one of our upcoming products. This will basically be a 1 megahertz to 6 gigahertz transceiver solution that's in a candy bar form factor. So it still is using the Analog Devices 9361 that's familiar to a lot of people, basically putting block up and down converters sitting in front of it, and then brick wall SAW filters at a high IF. So we're quasi-turning this into a super het design, kind of sorted with a ZIF block and then an up and down converter block sitting in front of it. The other benefit is this brings pre-select filtering even when you're not down at the lower frequencies where you're going to have the benefits of the filtering at the high IF. This brings pre-select filtering to the mix as well, so you can use this in applications that are more harsh than what maybe you're used to if you're running a radio that doesn't have pre-select filtering. Uses OpenWRT as the basis for the Linux OS that's on there, and you have the standard kind of array of interfaces with gigabit Ethernet, USB, and HDMI on there. And we have we have an AM radio demo at our booth if you want to stop by and check it out. The other piece, I mentioned modularity and scalability here, being able to really expand upon this idea of how do we take other commercial off-the-shelf cards and marry them up to the SDR and have a little package that can do something interesting. This has been something that we've thought about for a long time, and we're going to have a whole progression of devices available here that support multiple, think of them as multiple card slots, right? So little single board computers with well-defined interfaces on the outside and multiple card slots internally that we'll be able to deliver to customers for supporting different kinds of applications. So that could mean one SDR, that could mean 2 SDRs, it could mean Wi-Fi Bluetooth cards. It could mean putting 3G, 4G cell modems next to the radios. So it kind of opens up a whole array of possibilities, but at the end of the day, you get something that's about the size of a deck of cards, or a little bit bigger, that you can start to have all inside a unit supporting different use cases. So if you have a Wi-Fi card and a Bluetooth card and an SDR, that supports one use cases. We have other customers that are very interested in being able to do portable recording at very fast rates. So you put a terabyte MSATA drive right next to the radio inside the platform. That gives you a different version of the solution. But the core software, the core platform itself, kind of fits exactly into this mold of modular and scalable. And there will be 4-slot and 6-slot versions coming out as well, so we can continue to start to bring more radios in or more commercial devices, putting them right next to the SDR and having the entire system be a field usable, field deployable platform for customers that are interested in that. So 4.5 inches by 3 inches by 1.1. So again, keeping the focus on relatively small. Okay, so in the Sidekick family, traditionally we have focused on very small mini PCI Express and M.2, but in reality we kind of think about Sidekick as card-based solutions that we can put into other systems. So in that context, we're kind of first publicly talking about our next generation design, first design that uses the next generation analog devices, 9371. If you're not familiar with the 9371 analog devices booth, they've got some demos set up over there. This is the kind of the progression forward from the 61 that gets used in a lot of common radios, except it enhances several very key pieces of the radio lineup. So number one, it brings receive dynamic range substantially higher with 16-bit data converters on the receive and 14-bit on the transmit path. It opens up the bandwidths of the receivers and the transmitters substantially. Sort of minimum to be looking at on the receive is in the 100 megahertz range, and transmits get up to 200 plus megahertz, and there are options for even doing receive north of 200 megahertz as well. One of the things that we're doing with the chip is putting some additional circuitry around it. So this card, which is a standard FPGA mezzanine card form factor, will give you full coverage from the 1 megahertz up to 6 gigahertz. That same idea that we're doing with the Matchstick S12 of putting block up and down converters sitting around the 9371 to provide a solution that covers as close to DC to daylight as possible with high dynamic range, very good linearity, very capable noise figure in a relatively small package. That's kind of where our focus has always been, and I think this is going to be real interesting. If you look on the I/O of this guy, so this has a phase coherent receive pair, so you can basically do common LO receive. It has a third independently tunable receiver, which if you're familiar with the 9371, this goes into the observation port, which you can drive and use for observing other chunks of spectrum. And then a single transmit output, in addition to being able to bring in 10 meg and PPS input. So this will slap into different platforms that already are using the FPGA mezzanine card form factor. So this is used sometimes in 3U, 6U VPX solutions, which are kind of geared towards some of the more mil-aero solutions out there. But I think it's going to be a very interesting platform to bring to bear. And we've got one of these up at our booth if you want to come check it out to kind of put your hands on it. Last but not least, this is also going to be the new card that gets rolled into our next generation quadratic platform. So if you're familiar with our current quadratic platform, it's a box about the size of a cigar box with a radio FMC card internally, and current generation has a Zinc 7030 or 7045. This platform bumps up to use the same Sidekick X2 card I mentioned in the last slide, combined with the Zinc UltraScale MP sock. So the first versions, we got our first few boards in with a ZU9 on them. If you're not familiar with Zinc's UltraScale lineup, it is a relatively massive step forward, both in the CPU side as well as the amount of FPGA resources you get available to you. So the first chips that are shipping, the DSP slices are north of 2,500, which is a pretty big deal. Logic blocks and block RAM go up as well. So you basically end up with a massive FPGA sitting behind a reasonably capable quad-core CPU and a radio front end that can feed it all day long from near DC to daylight. So we're really excited about this. You get dual 10 gigabit Ethernet coming out these ports here. So if you want to stream Vita49 all day long, that gives you one path. If you want to keep the processing local in the box and get it up to the CPU and do everything there, that gives you another path. And then there's a single gigabit Ethernet interface for interacting with the unit as well. So in summary, right, SWaP is a big deal. We're trying to push as hard and as fast as we can to have this be at the forefront of where SDR moves and progresses forward. We think that it should be a first-class citizen right next to writing the software. I know there were some discussions, I think, on Monday about, like, does the radio even matter anymore? Yes, the radio matters. If there's any confusion, we can assure you this, especially as people go out of the research land and move things into the real world and start deploying these systems. The radio makes a huge difference. A lot of this work, like I said, it's kind of focusing on how do we get the RFIC and the FPGA working better together so that the CPU load is going to be manageable. And the proper system partitioning is kind of the key there. So that's all I got, and I think we've got lunch next. So
we have time for questions.
Yeah, if there's any questions, I would be happy to answer.
Okay, questions for John.
I have a question and an offer. What's the tool flow you use? And if it's ISE and system generator, we have a 802.11ac transceiver full design that we're more than happy to share.
Cool, yeah, so on the Arctic side and on the Zinc UltraScale side, they're forcing your hand to Vivado. If you've used, Vivato's good. I mean, Vivado has its benefits. It has a little bit of challenge to making it work as well. I'd be interested in talking a little bit more, even comparing notes about what you're doing with that, because I think it could be an interesting overlap with some of the work that we're doing. The work that I mentioned there, in particular, it's sort of a collaboration with another one of our customers that was interested in kind of pushing the limits, but the outcome of that would be that we could take and use and license however we wanted the output. So being able to get it into other customers' applications and people that wanted to use it with GNU Radio, we can still kind of keep the boundary where the GPL side of software is happy and do things down in the FPGA that doesn't necessarily have to be GPL compliant for customers that want to ship and not have that piece be held up.
Thank you, Dirk. Any other questions? One over here.
What kind of clever tricks do you do to keep the noise of the CPU out of the RF deck?
Excellent question. Yes. Last year's slides, if you were here at the conference last year, we did a presentation about embedding SDRs inside of laptops. Right? Since these are mini PCI Express cards or M.2 cards, they are going to be sitting intimately close to the radios or to the CPUs themselves. So one of the plots we showed was we had a Core i7 3 inches away drawing 35 amps at roughly a volt at maximum processing, and then we did a spur sweep to basically show, let's see the spurs up and down the lineup, and what do you have? And the loudest spur that you could see was the fundamental of whatever the CPU was running, and I think it was running at 2.5 or 2.6 gigahertz at the time. It was peaking up about minus 95 dBm, and everything else was below that level. So you've got a couple of things working for you, right? When your whole radio is this big, there's not a lot of areas for antenna, not a lot of traces, and not a lot of components that can start acting like antennas because the physics of the situation is really pushing. You just don't have a lot of places where the RF's going to get in. We put shields on these. The shields, you can see a notable degradation if you do not have the shields on the system. Combining that with a lot of the work that's happening just on the RFIC integration itself, the physics are in your favor in terms of trying to keep unwanted signals from getting out. So it's good layout. I mean, these are 10 and 12 layer boards with blind and buried vias and very complicated stack-ups. That makes a big difference when you need to fit everything in this kind of form factor as well.
Any other questions? Nope. Okay. Let's thank John.
Thank you, guys.
Thank you very much.